Okay, so here we go with paper 2, and let's work our way through this one. So some usual stuff. They usually start with some nice binary questions, so we'll start with this one. Convert the decimal number 197 into binary. Now remember the way I showed you to do this, to start on the right hand side and just keep dividing by 2. So 197 divided by 2, again drop the is 98, drop the remainder. 98 divided by 2 is 49, divided by 2 is 24, remainder 1, but drop the remainder. 24 divided by 2 is 12, divided by 2 is 6, divided by 2 is 3, divided by 2 is 1, remainder 1, stop there. Write 1 under each odd number and 0 under each even number, and that should be the answer. Now at the end, always a good idea to quickly check. So 1, 2, 4, 8, 16, 32, 64, 128. 128 plus 64, 1, 2, 4 plus 4 plus 1. 128 plus 64 is 192. 192 plus 4 is 196. Plus 1, 197. Okay. Convert the hexadecimal number A4 into decimal. Show your working. Now, they'll give you the marks if you get the answer right. Show your working to get a mark if you, by some freak of mathematics, got it wrong. So remember the 2 digits. These are units and these are 16s. There are 4 units, that's easy, and they're A16s. Remember A equals 10. So 10 lots of 16 is 160. 4 lots of units is 4. 160 plus 4, 164. What is the largest decimal number that can be represented using 5 bits? Well, the largest number must be 1, 1, 1, 1, 1. 1, 2, 4, 8, 16. 16 plus 8 is 24, plus 4 is 28, plus 2 is 30, plus 1 is 31. Notice that the next one along would have been 32. If you fill up this, it's always 1 less than what the next one will be. How many bits are there in 3 megabytes? 3 megabytes. Mega, a million. So 3 million bytes. And again, you'll get a mark for just writing that down, to be honest. Remember, showing your working. If you get it wrong, you've got 2 marks, 1 mark for showing any working at all. How many bits are there in a byte? There are 8 bits in a byte, so we'll multiply that by 8. So pull our zeros down again. 3 times 8 is 24. There are 24 million bits. Moving on, next page. Okay, state the decimal representation of the binary number 100101010. Right, so 1, 2, 4, 8, 16, 32, 64, 128. So the answer is 128 plus 16 plus 4. 128 plus 16 is 144, plus 4 equals 148. No marks for working on that one, right answer or not. State the hexadecimal representation of the binary number 10010100. Now remember the trick here with hexadecimal. Divide the number into two parts. 1001 is 9. 0100 is 4. So the answer is 94 in hexadecimal. State the hexadecimal representation of the decimal number 143. Now, there's a couple of ways we can do this. The first one is we can just divide it by 16, if you feel confident with your 16 times table. So 143 divided by 16. Well, there are 8 116s in 184. Remainder 15. So remembering that means there are 8 lots of 16 and 15 units, which is 8. Now we can't write 15, we write F. Remember in hexadecimal, F is 15. That's one way of doing it. The alternative way is to convert 143 into binary. Now I'm not going to go through the process, but if you do that in binary, you'll end up with the number 0, 1, 0, 0, 1, 1, 1, 1. Split that up. That is, sorry, I've got it completely wrong. That's 1, 0, sorry, 1, 0, 0. That would be 8, and that will be 15, which is F. Two ways of doing it. Either way, it's perfectly valid. State the binary representation of the hexadecimal number BE. Again, remembering each hexadecimal number is 4 bits. So B, A is 10, B is 11. E, A is 10, B is 11, C is 12, D is 13, E is 14. How do we show 11 as a binary number? We show it as 1, 0, 1, 1, 1, 2 and 8 makes 11. 14 we show as 1, 1, 1, 0. And there's your 8-bit number. 1, 0, 1, 1, 1, 1, 1, 0. 2 marks. Again, anything of this or any stuff like this will get you a mark. You've got 2 marks for each one. Do show you're working. Over we go, onto the next page, and we're on to other stuff. 2 reasons why hexadecimal is often used instead of binary in computer science. So why do we use hexadecimal? Why do we bother to learn it? Well, 2 marks, so you only got some state here. You don't have to give any reasons. So you can say it's easier for humans to understand. That gets you a mark. Than binary. So far so good. That's 1 mark. Okay, why do we use, so if we want it to be easier, why don't we just use tens? Why don't we use decimal? Well, the reason we use hexadecimal is each digit shows 4 binary digits. Remember, as we've shown before, each hexadecimal digit, it just shows you what's in 4 binary digits, and therefore it's much easier to see what's on the underlying binary code, even though you're using a much higher level code. Okay, now again, add together 3 binary numbers and give your answer in binary. Again, very important to show you're working. 2 marks here. You get both marks if you get the answer right, but the important thing is show you're working. Then if you get the answer wrong, if there's evidence that you know what you're doing, you'll get at least something. 1, 0, 1, add those together, that makes 2. 2 in binary is 1, 0. So we put down the 0, we carry the 1. 0, 0, 0 and 1 is 1. So put down the 1. 1 and 1 and 0 is 2, which is 1, 0 in binary. So we put down the 0, carry the 1. 0, 1, 1 and 1 is 3. 3 in binary is 1, 1. So we write down the 1 and carry the 1. 1, 0, 1 and 1 is 3. That's 1, 1. So we put down the 1, carry the 1. 0, 1, 0 and 1 is 2. 2 in binary is 1, 0. So we put down the 0, carry the 1. And finally, 1, 1, 0 and 1 is 3. 3 in binary is 1, 1. Put down the 1, carry the 1, 1. And there's your answer. State the result in binary of performing a binary shift 2 places to the left on the binary value, da 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 da. So all we've got to do is move all these numbers 2 places to the left. So you can see there are 2 zeros there, so all these 1s will move 2 places over. So there's 1, 2, 3 1s, then they're followed by 2 zeros. So there's the number shifted 2 places to the left, and we fill in with zeros at the end. 1 mark. Right or wrong? Number 5, state, again, no need to give a reason. State one advantage of using Unicode instead of using ASCII. So an advantage of Unicode, remember Unicode is has more bits, a much bigger character set. So you can put down something like, includes many different characters from different languages. That's the obvious one, isn't it? So whereas ASCII only uses the Western alphabet, A, B, C, D, Unicode includes many, many different characters. The disadvantage, of course, is because it's a larger character set, it uses more bits. Which 2 of the following are components of a CPU? 2 things here. Arithmetic logic unit, yep, we'll go for that one. ALU is in there. Control unit, yep, that's in the CPU. Well, it looks like we're winning already. Let's just check the others, make sure. Fan, no, that's hardware. Hard disk drive, no, that's storage. Keyboard, no, that's an input-output device. Power supply unit, that's just a bit of electrical gubbins. Yep, none of those are in the CPU, so we're right with the first 2. There we go. Number 7. Shade 1 lozenge to show which statement best describes data compression. Compression making smaller. The process of calculating the file size. No, that's nothing to do with making things smaller. The process of encoding characters into more than one language. No, that's not making anything smaller. The process of encoding information to try and use fewer bits. Fewer bits, that's smaller, isn't it? Yeah, that one. Fewer bits. The process of removing necessary data from a file. Well, we certainly wouldn't want to remove necessary data, would we? Forget that. Give 2 reasons why data compression is often used. Well, 2 classic answers. Saves storage space. So if you want to use your space more efficiently, if you've got a small space and you want to be able to store more files in it, compress them. And secondly, files you want to download, obviously you want them to be as small as possible because it speeds up download times. Notice that using compressed files doesn't make them work faster because you have to use up time to decompress them. So just be careful not to talk about speed in terms of actually opening the files, but it certainly makes it quicker to download them. Now, we didn't do too well on this one. I want you to go back and revise RLE more carefully. Run length encoding. Remember, that's the one where you work through and where you find a block of things, instead of showing each thing, you take you say there is one thing and there is this many of them. So if you had a number that had sort of 1 1 1 1 1 1 0 0 0 0, you wouldn't write that down. You would just write that there are 1, 2, 3, 4, 5, 6 ones followed by 1, 2, 3, 4 zeros. And that makes life much smaller when you have large blocks of the same. State the feature of data that allows it to be compressed effectively. Well, that's when you've got large blocks of the same data. So when you've got large blocks of similar data or the same data, like when a large block of ones or a large block of zeros, then it makes much more sense to use RLE. Describe how RLE works. In your answer, you must use an example. Well, there you are. I've used an example already, so I'm not going to write it again. And you count how many of the same data there are, and only list it once. And then you can use this example to show that. 1 mark for the statement, 1 mark for the example, bang, done. 2 marks. State 3 lozenges to show which of the following are essential components of the von Neumann architecture. So what do we need to have a fetch execute cycle, basically? So do we need a BIOS? No, the BIOS is to make the computer start. A control unit? Yep, we need a control unit because we need something to do the decoding. Keyboard? No, computers don't have to have a keyboard. Memory? Yes, we need memory. There needs to be somewhere to store the program that we're going to use. Movement sensor? No, that's an input device. Multiple cores? You don't have to have multiple cores. Network socket? No, we don't need a network. It can all be self-contained. A shared bus? Yes, there must be a shared bus because the data has to be able to move around in the fetch execute cycle from memory into the CPU. 1, 2, 3, control unit, memory, shared bus. Main memory is any form of memory that is directly accessible by the CPU, except for cache and registers. So basically it's talking about RAM and ROM. In this case, RAM being what we're really talking about. So we've got a clue from up here that we're talking about the fetch execute cycle. So to get our 3 marks, we basically need to state that instructions are fetched from memory via the bus into the CPU. So we've got 1 mark for the fact that we're fetching instructions from memory, 1 mark for saying that we're using a bus. So after processing, data is sent back along a bus to be stored in memory again. So the idea is that we need to be aware that data is flowing from the memory into the CPU, being processed and then sent back to be stored in main memory. 3 marks. Okay, let's have a look here. We'll just do I think we'll just do up to page 10 on this particular video, and then we'll come back to finish the rest in the next one. Select the correct statement about secondary storage. Secondary storage is a type of ROM. No, doesn't have to be. It can be RAM or ROM. It can be volatile. It can be a or not volatile, but it's certainly not ROM. ROM is read-only memory. Secondary storage is non-volatile. Non-volatile. When you switch off the computer, is what's in secondary storage still there? Yes, it is. It's non-volatile. Secondary storage is temporary. No, the whole point of having secondary storage is that it stays there whether the computer is switched on or switched off, whether you're carrying it from one place to another or not. Secondary storage loses its content when it's turned off. No, it doesn't. It's non-volatile. So that's wrong. This is the correct answer. Secondary storage is non-volatile. Now describe how an optical disc is read. An optical disc, a CD or a DVD, how are they read? Well, we need to get 4 marks here. So first mark you'll get for saying that a laser shines on the disc. Next one, you can say that the disc spins quickly. Data is coded as bumps and sort of valleys, we can call them, or lands is the more posh term. So data is coded as bumps and valleys as the reflection of the laser returns. This is read as ones and zeros. 1, 2, 3, 4. Next one. Right, we move on to another kind of storage medium, the magnetic hard disk drive. So let's have a look and see what says here. A magnetic hard disk spins very quickly. We've got 3 factual errors. A magnetic hard disk spins very quickly. True. The surface of the disk has a groove on it. False. There are no grooves on a hard disk. It's just a coating of metal oxide. So first one, the groove on it is false. Where data is stored. There is a needle that runs along the groove, and that's a vinyl record. That's not a hard disk. So there is no needle. So needle in groove, that's factually. And detects bumps. No, there are no bumps. That's going back to the optical drive. One of the components of the drive is a read-write head. Yes, that's correct. The read-write head goes across the hard disk to read the magnetic state of what's on the hard disk. State one correct fact in the description. Well, there are 2 correct facts we could pick up here. The magnetic hard disk spins very quickly. That is true. And there is a read-write head. Either of those is correct. Spins quickly, or the read-write head, not read-write, read-write head. Either of those will get you your mark. Shade the 2 lozenges that are correct statements about RAM, random access memory. It is only used in solid state storage devices. Wrong. It's used in lots of things. It is used for main memory. Yep. It is used for secondary storage. No, secondary storage is things like hard disks, CDs and so on that aren't connected directly to the CPU. It is volatile memory. RAM is volatile. Once you switch off the computer, what's in RAM is lost. It never loses data. Well, that's the opposite of D. It does lose its data. It permanently stores programs and files. No, because it's volatile. So that's ROM, not RAM. So that one's wrong as well. So the 2 correct ones are it's used for main memory and it is volatile memory. Question 12. 3 factors that affect the performance of a CPU are clock speed, number of processor cores, cache size. Explain. So get your marks by giving a reason how each of these factors affect CPU performance. So basically we need to state whether increasing or decreasing will make things better, faster, and then we need to say why that is so. So clock speed, increase clock speed, and the computer will get faster. Because, there's your second mark, more instructions will be processed per second. If the clock speed goes up, so if it's just ticking, tick, 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 for each instruction, then if you turn the clock speed up, then the instructions will be being executed, tick, 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 so more instructions per second. Number of processor cores. So increase the number of processor cores, and it goes faster. There's one mark. Because, why? Because more instructions can be processed, and now here's your critical one, at the same time. So instead of doing one instruction at the same time, instead of only being able to do one instruction at a time, as you would with a single core, if you've got a quad core, you can load 4 instructions, and all 4 will be being processed at the same time. Cache size. So increase cache makes the computer go faster, because recent instructions can be stored, so no need to fetch them from memory. They're nearby, so they can be immediately accessed, which means you save on clock cycles bringing in the instructions. Okay, so far so good. We're up to question 12. The rest we'll deal with on the next video.